This is part 2 of how amines, our amine chapter. So we've covered how amines are basic and what affects their basicity, and we've covered how to make amines. Now we're going to talk about reactions that we can use with amines. Some of them are going to be review. The main thing to remember is that amines have that electron pair, right? So that makes them electron rich, and so they are nucleophiles. So then the question is, what kind of electrophiles can we react with them? And that's what we're going to look at. So a lot of this is review, right? Amines and carbonyls. Carbonyls are a good electrophile. So you can have the formation of amines and enamines right through this tetrahedral intermediate. So this is with a aldehyde or ketone. And then if you have an acid chloride or an ester, you can react your amines to get the substitution product, which is the amide, right? So these are addition products, and that's your substitution product. And for this one, remember we looked at 2 equivalents of the base or 1 equivalence of your amine plus 1 equivalence of a non-nucleophilic base. So either or, either 2 equivalents or 1 and then a helper base. So this is all review from the last chapter, the carboxylic acid chapter. So I'm not gonna go over that too much, but one thing that we didn't really cover when we were studying aromatic reactions is that amines interact with Friedel-Crafts. They basically make it impossible if you have an amine on your benzene ring, instead of just adding, say, an alkyl group through a Friedel-Crafts alkylation with aluminum chloride, right? You would expect donating group, so ortho para, but it actually doesn't happen because you end up with the nitrogen complexing with the aluminum chloride. And once it's now, you get this complex, this charge complex, it actually makes the nitrogen very electron deficient. Right? And that in turn pulls electron density from the ring, which in turn deactivates it. Right? Because in this reaction, right, benzene is the nucleophile. Right? It needs to be electron rich to attack the alkyl chloride. So if you have this very withdrawing group, basically now the nitrogen is positively charged, he's electron deficient, he wants that electron density from the ring, and what will happen is that the ring will just not be electron rich enough to make this reaction. So in the end, you think you've done it, but then you quench with water and you lose the aluminum chloride complex and you just get your starting material again. So what do? If you want to keep building on your benzene ring and you have an amine, well, you do a protection group with an amide. So we've seen, right, an amine with an acid chloride reacts readily to make an amide, right? This is your and now you can do Friedel-Crafts acylation or alkylation, and there's no problem, right? And there's no way to complex on the nitrogen anymore. You're not going to form the aluminum chloride complex. And so this group is still an electron donating group vis-a-vis the benzene, right? So this will be ortho-para directing. So that's why you get, ortho and para product. And then if you don't want that amide, right, it was just a temporary thing, you deprotect, right? And so we've covered this. This is just an amide hydrolysis. Right, and so you can get back to the amine. So an extra step to get to your desired product, but right, we didn't really cover this before when we were doing benzene chemistry, because then we would have had to explain amide synthesis, and we weren't ready to do that. But it's important to note that now when we're revisiting benzene chemistry, if you have an amine, you cannot do a straight Friedel-Crafts. So I'm going to do a couple practice. I'm going to do one, and then I'll let you guys do the other one at home. So they want us to start from aniline, right, and synthesize the compound. And these are just exercises to show you that you cannot just do straight Friedel-Crafts. So I have NH2, that's my aniline, and I cannot just say, aluminum chloride, I'm going to do like a straight alkylation. It's like, no, this is the thing you cannot do now that you know better. So instead, we're going to do the protecting route. We're going to react with an acid chloride. It doesn't really matter which, because we're going to remove it at the end. This is so reactive that you really don't need anything else. Oops, sorry. I'm going to make the amide this way. Right, so still one hydrogen there. And now we can go ahead and do what we wanted to do with the Friedel-Crafts. And this will give us both the ortho and the para. But the ortho in this case, probably very minor, because of the sterics of that tert-butyl group, right? So this is a bulk of T-butyl. So this will be minor, and then what we want will be our major. Right, that'll be our major product, and then we will have to remove the amide. So this will be major. And then we will get the product they want. So we go back to the amine, and we've installed that tert-butyl group. Okay, so I'll have B posted in the notes. All right, so now we have a new electrophile that we have not seen before. It is called nitrous acid, and we call it HONO because nitrous acid is this nitro group with a hydroxy, so it literally is HONO. This is So whenever you see one of these reactions, you're generating your electrophile in situ. That means, in the in the reaction pot. But here's a quick overview of what's happening. So you start with sodium nitrate, and it will react with usually an inorganic acid. So normally probably HCl is a good one, but it doesn't have to be. It will become protonated into HONO, the nitrous acid. And now once you have nitrous acid in the pot, nitrous acid also, with these acidic conditions, become protonated again, right? It is a weak acid. And it becomes protonated, and here it basically forms this water leaving group. Which comes off, and now these are all reversible, and then you form the nitrosonium ion. And this is actually your electrophile. So the reaction conditions may just be sodium nitrate and some HCl or some aqueous acid, right? But what you're actually forming as your reactive species is this NO+, this nitrosonium. This is your electrophile that your amine can react to. What does that make when you have an amine that reacts with an NO? You get a diazonium salt. So azo is referring to the nitrogens here, so it's a diazonium salt. You can do this with a primary alkene, and you'll get a primary alkyl diazonium, or you can do it with an aryl amine, and you'll get an aryl diazonium. Now, just by looking at these structures, you probably guess these are not very stable. The alkyl diazonium, really not stable. It's generally not synthetically useful. The aryl diazonium, it's also not super stable, but basically at 0 degrees, it's okay. Basically below 5 degrees Celsius. So if you make it in situ in a really cold reaction, it can be used. So all of these will always be aryl diazonium. Do not use alkyl, right? So what does this mechanism look like? So I put HCl here, but basically, or other aqueous acid would work. So our nucleophile is our amine, and I will maybe shorten this to be, and our electrophile is the NO. And so it's this lone pair that attacks at that nitrogen. It's the nitrogen, this one, that is electron poor, right? So this right here is this is my nucleophilic nitrogen. So one nitrogen attacks the other. You get, I'm gonna just write phenyl here. So we still have the two hydrogens, and then we're bonded to the NO. And now we have, HCl in the pot, right? So here it's going to be deprotonated by some of the counter ion. Oh, right, sorry, I forgot to write the positive charge, right? The originally positive charge, which is why it needs to be deprotonated like that. And then we reform HCl, right? These are acidic conditions. And then this oxygen will become protonated. So now it carries the positive charge, but there are all these nitrogens here in conjugation with this, with that oxygen, right? So you will form a double bond between the two nitrogens and break the NO double bond. And here I'm just going to draw the resonance structure, right? So forming that double bond, and then double bond to the nitrogen, single bond now to that OH. So he's no longer positive, but now this nitrogen carries the positive charge. Okay, so that's just resonance between these two. And we have generated more chlorine minus again, which will help deprotonate here and neutralize that nitrogen. Okay, and then we reform HCl, and then this oxygen wants to be protonated again. We'll steal another hydrogen. Now we have that OH2, that water leaving group, and again, all these lone pairs. So here we're going to form a triple bond and boot off the water leaving group, right? H2O leaving group here. So lose water and you get nope. Now you have that triple bond, still that lone pair on the end, and now this nitrogen is positively charged, and this is your aryl diazonium. And because this is a charged species, there's always that counter ion present. In this case, it's chlorine, but again, depending on what acid you used, it could be different. Okay, so that's the mechanism with an aryl amine. Now, this is a primary aryl amine, right? This is primary. What if you had a secondary amine, right? So you could start this reaction off and it would work fine, but you would end up at this reagent. So this is a nitrosamine. It's very carcinogenic. It does have some applications, but not ones that we're going to discuss. So why do you stop here, right? Well, that's because with a secondary amine, you can't do this step. Right, this hydrogen is not present to deprotonate. This would just be an R group, and then you wouldn't be able to deprotonate and continue to form the water leaving group and kick it off, right? You wouldn't be able to form this triple bond with the nitrogen because this nitrogen would have, some other R group here. So the reaction does work, but doesn't go all the way, and so it's really not really that useful. And also just to point out, right, so when you see these, this is when you see sodium nitrate and HCl, you should think, right, that's going to make HONO, and that's going to make your NO+, right? But you're making all of that in situ, so the reagents will still be just sodium nitrate. So here's a set of problems. I'll do the first one, right? So just as I was saying, sodium nitrate and HCl, right? That equals a HONO electrophile. And let's do the first one. Basically, we're just turning each amine into the corresponding diazonium. Of course, careful here, right? Some of these are secondary amines, and so you might not be able to get as far, right? We just covered that. But the first one is a primary, so pretty easy. My plus, don't forget my methyl group, and they said HCl, so I will write my chlorine minus. Right, so I'll post the rest on the slides. Go ahead and give it a shot now. Now, why do we want to make these diazonium salts? They seem a little funky. What do we do with them? They are good for two really amazing things. The first are, it's called replacement reactions. We say replacement because we're not going to teach you the mechanism. It's not SN2, it's not an electrophilic aromatic substitution like we studied in chapter 16. So for now, it's just a replacement. But what's really neat is basically with a series of reagents, we can just introduce that reagent onto benzene, kick off and nitrogen gas, right? So this goes really well, drives that reaction forward, and this lets you make some new benzene derivatives that we have not seen before. The other one, the next reaction is diazonium coupling reactions, and these are actually electrophilic aromatic substitution reactions, so the same mechanism that we learned in chapter 16, and you form these cool azo compounds here, and we'll see those as well. So let's start with the replacement reactions. Here they all are. Now you don't need to know the mechanism at all, but you should know your reagents, right? And you can see that you can make a really wide variety of things. So you can make a phenol. If you can, this is a different way of introducing chlorine or bromine on benzene. This is called the Sandmeyer reaction with copper. And then, so if you want to introduce fluorine and iodine, remember we were not able to do this before. These are new. Also, you can add a cyano group directly onto benzene. And then if you wanted to get rid of your diazonium hypophosphorus acid, we'll just give you back hydrogen and give you back your benzene. So basically these three we have not seen how to do before. Right, for being able to make them. So that's new. And this just lets you make a wide variety of benzene derivatives. Okay, how about diazonium salts in coupling reactions? So again, this is going to be our, it is an, sorry, I put ears up here, right? It's electrophilic aromatic substitution. Okay, so who is the electrophile, who's the nucleophile? Benzene is going to be the nucleophile, and our diazonium, right, now really electron poor, is going to be our electrophile here. Okay. Now, this works if you have, importantly, that para-electron donating group. That is important, and we'll see that in the mechanism. So here's here's my diazonium. Again, chlorine's still hanging out. And then we're going to add so as a donating group, we're going to do hydroxy. And basically this gives the benzene ring that, a boost of electron density. And then the benzene ring is our nucleophile and going to attack, going to attack this nitrogen. And there, and break that triple bond. This gives you para addition. So we've temporarily broken our aromaticity here. So para addition. We still have that handy chlorine salt here that will now deprotonate here, and then we will reform that double bond, and there we go, and then reform our aromatic ring. So the final compound so this is an azobenzene product. This group here equals an azo group. So azobenzene products are really cool. Now this isn't going to be on the test, but I kind of have to talk to you about these. So famously, azo compounds are dyes, very colorful. And what's neat is that the electron donating group that you use will change their absorption and the color of the dye. So here, this azobenzene with the hydroxy group is bright orange, but just same thing, azobenzene with an amine is yellow, right? So that substituent. Right, so it will affect what colors the dye emits and also absorbs, right? So it'll change its color. And you can make these, these azo compounds pretty complex. It does work with other aromatics, right? Doesn't necessarily have to be benzene. This is yellow 5, tartrazine. And so it's obviously in a lot of foods and Doritos, I think, and Kraft macaroni and cheese. It's a bright orange dye. But what I thought was kind of cool, and you can check out this description, this was the molecule of the month a while back, was that originally, old paintings used Indian yellow, which was a magnesium, calcium salt with this other, this is another type of dye. And this was sort of expensive pigment. And then when they discovered tartrazine, it became available as a dye, and so that's used in more modern paintings. And so this is an easy way to tell if a painting is a fake, right? Because if you do Raman spectroscopy and you see that it has this azo molecule in it, then you know that, it's, well, not that super modern, but at least it's like not like an ancient, I don't know, a very old painting. So I thought that was neat. So azo compounds are in dyes, but they also do a really cool thing, is that azobenzene compounds can switch. So here you can see how they're all in this trans form, right? But you can flip them between trans and cis, depending on whether you shine UV light or visible light at them. And they switch back and forth without degrading really that much. And so this is work that was done by a professor at McGill. Actually, a good friend of mine worked on this. So they're making a fairly large azobenzene compound with some alkyl groups on the ends. So these are kind of long chains. So they're making a material that they can spin into a film. But you can see here, like, they have the amine, and they are doing the diazonium coupling, right, with your HONO to get your azobenzene. And what they did is they put it on a film that's flexible, and then this is a motor, and they shine, I think, UV light this way and then visible light this way. So as the strip with the azo compound is going around, it's being switched from cis and trans. And as it switches from cis and trans, it literally moves. Like, the whole molecule goes from, being trans, which is sort of linear, to cis, which is more like bulky, like more bent, right? And so let me see if I can switch over to show you this video. But basically, as that happens and as the film flexes, it moves the motor around, and you can see this is like slowly pushing the motor, and this is why they call it a light motor, because you're using light to spin the motor. Is this energy efficient? No, not terribly, but it's super cool. And other labs have made like very thin sheets of azo compounds that will like sort of flutter with light. So you can Google azobenzene motors, and there's some cool stuff there. Okay, for you pre-med folks, have to also mention that these azo compounds were some of the very first chemotherapeutics, so giving basically a medicine to treat a disease. So this azobenzene structure it's called prontosil, and it was first used by Gerhard Dogmack to treat streptococcal infections before there were antibiotics. And so they were known as dyes before, but he was like, well, let's try using them as medicines. So he tried on mice first, and he found that it didn't cure, it didn't kill off the bacterial infection, but it stopped its growth enough that the mice recovered. And so prontosil was very, very popular and one of the first medicines used. And Domag won the Nobel Prize in medicine for it. But it wasn't until actually not too much later, but it was actually French chemist Ernest Fourneau who learned that it wasn't really the azobenzene structure that was having the effect. It was actually the cleaved product, right? If you cleave here, you get this amine. Well, it's a sulfanylamide, right? So this is the sort of amide group here, and this is actually the active compound. Right, and so that makes pronosil completely by accident, but one of the first prodrugs. A prodrug is a drug that's administered in an inactive form, which you might want because it will be more stable. You could have it, in the pharmacy for a longer amount of time, and then also it only starts acting when it's in your body, and so it has an inactive form, and then it's metabolized in vivo, so in your own body, and becomes the active metabolite. So in this case, it's an azoreductase enzyme that generates this structure, which is your actual drug that is doing the healing. So sometimes eating dyes can be good. I'm gonna have more Doritos. Okay, so this last one is the Hofmann elimination. It's in your book, and I think you should have covered it a little bit in Organic 1. It's not a super useful reaction, so I'm not going to test you on it, but I did want to say that, this is ACS content, so I want to show it to you. Basically, it is, you start with an amine, and then SN2, right, you react with an electrophile. This is your RX electrophile, just like we saw at the beginning with the preparations of amines. And you do use an XS, all right, XS, and that gives you that ammonium salt, right? It goes all the way to the ammonium salt. And now you have this really bulky group. Also, so you deprotonate, so you get HI as a side product. Right. And so then you have this large bulky group, and if you now want to do an elimination, you use a strong base and heat. And because this is so bulky, instead of generating the more substituted alkene, where you would have to deprotonate over here, right? That would give you the more substituted product, which normally is the major product. But because this ammonium salt is so big that you'll actually deprotonate on the less substituted side, and you get what's called the Hofmann product with the less substituted alkene as your major product. So that's the main thing that you need to know, basically, is that Hofmann product means less substituted alkene. But synthetically, it's hard enough to get an amine on your compound, and then you have to distill it over this base. It's not a reaction that is very typical and not the best way to make an alkene. So we're not gonna use it for our synthesis. But you should know, if you see on a test this sort of question, right, with an amine forming an alkene, if you're going via this route with via the alkyl ammonium salt, then you're going to get the less substituted alkene. And now we're at a bunch of book problems. So I'm going to leave it here and fill these in, and we can discuss it at our Zoom session. Okay, thank you.